Are you able to see my PPT?
Yes, sir.
Okay. So this is what we were discussing. So we have started this equation of change in last class. So equation of continuity is needed to discuss the equation of change that we have discussed in last class. So today we will discuss this equation of change. So what is this equation of change? Is nothing but a shell balance approach. So in previous section where we were discussing shell balance approach, we have discussed it for simplified form, actually one dimensional flow and one directional variation. But equation of change is same shell balance approach applied for generalized form, actually all three velocities and all three directional variation. And then once we got a generalized equation, then we can substitute all these assumption, and again same problem which we have solved in previous problem can be solved using this. Even we can handle a complex problem also using equation of change also. So simplified shell balance approach, which we have seen in this thing actually last section, okay, that may not be able to handle effectively when we have two dimensional flow and varying in more than one direction. So that's what this we were discussing equation of change. So certainly if we have three velocity components, a three velocity component can consider any cylindrical coordinate system, Cartesian coordinate system, or spherical coordinate system. So Cartesian coordinate systems are very simple to handle. So we'll start with the Cartesian coordinate system. If I have all three velocity and it is varying in all three directions, so what will be the dimensions of differential shell? Roll number 15, Ali. Sai. Roll number 15, Sai.
Hello, sir.
Yeah.
Sir, dimensions means x, y, z, like that, for a cube.
Differential dimensions of a differential shell. If I have all three velocities and if I am having variation in all three directions, and Cartesian coordinate system, what will be the dimensions of differential shell?
Dx, dy, dz, sir.
Delta x, delta y, delta z. And how many equation you are expecting in momentum balance? So this is what we were discussing, equation of change. So what will be there? So rate, this will be accumulation of momentum. This is rate of momentum coming in my differential shell. This is the rate of momentum going out of my differential shell. And this is all external forces acting on the fluid. Generally, this will be gravitational force. This will account for a generation and consumption of the momentum. Okay, this is account for a generation and consumption of the momentum. That will be equals to accumulation of the momentum, rate of increase of momentum. So how many equation you will get? Balance equation. Here roll number 17, roll number 17, Leshma.
Sir.
Yeah, how many equation you will get?
Sir, in x direction we'll have 5xx.
Okay.
In y direction 5yx, and in z direction 5zx we'll have, sir.
Okay, but how many momentums are there? Likewise, you will get three different equations. One equation will be for x momentum, one equation will be for y momentum, and one equation will be for z momentum. X momentum will have three components. So x component of x momentum, y component of x momentum, and z component of the x momentum, that will account in x momentum. Similarly, I will have x momentum of y momentum, x component of y momentum, y component of y momentum, and z component of y momentum. And similarly, we will have x component of z momentum, y component of z momentum, and z component of z momentum. So there is one equation which will be defining x momentum, another balance equation will be defining y momentum, and third balance equation will be defining z momentum, and we need to solve simultaneously. These three equations will be solved simultaneously to get the x velocity, y velocity, and z velocity. That is what overall solution is there. So to start with, and as we are telling, okay, this is the generalized momentum balance equation. So consider a x momentum, and now x momentum accounts for a x velocity. So we are considering x velocity. So and its component in x, y, z. So all it is varying in all three directions. So certainly a dimensions of differential shell will be delta x, delta y, delta z. Roll number 18. Roll number 18.
Yes, sir.
Ashish. So what will be the component of x momentum and perpendicular surface area to that momentum? How to get rate first of all? Roll number 18, Ashish. Rate
Yes, sir.
of
Hello.
momentum coming in.
Sir, rate, sir, yeah, we will multiply flux with area.
Very good. Flux with area. So which component of flux multiplied by which surface area? Can you just tell me?
So for x-axis, no?
X momentum, not x
Oh,
axis.
okay.
X
Okay,
momentum.
sir. For x momentum, sir. Mm, sir, phi xx
Pi
and
xx multiplied by
and
surface area will be?
area will be delta y into delta z.
Very good. Then
Then sir, phi yy. For
why?
no, sir. Like delta y into delta z for x equal to x and then x
No,
plus
no, no,
delta x.
why you told, na?
No, sir. Sorry. Phi xx, phi yx, and phi zx for
So
three
what will be
three
the
in.
surface area perpendicular to phi yx?
Sir, for phi yx, it is delta z into delta x.
Very good. And third component of x,
Sir, then
x
it is
momentum will be?
delta x into delta y.
No, no. What will be the component?
Phi zx.
Phi zx. Okay. And how to get this rate of increase in momentum? So first of all, momentum. So how to get momentum? Rate of increase in momentum. If I have x velocity vx, so
Yes,
what will be the momentum?
sir. Like for momentum. MV MV.
Yeah, mv. So what will be the mass of the differential shell?
Sir, mass will be
How to get mass of the differential shell?
rho into V, or density into
Rho
volume.
into volume. How to get volume
Yes.
of a differential shell?
Sir, delta x, delta y, delta z.
Yeah, so this will be a dou by dou t, variation of change of momentum with respect to time. And how to get momentum? Momentum will be delta x, delta y, delta z. This is volume multiplied by density. This will be a mass multiplied by Vx. That will be a rate of increase in momentum. So that will apply for x momentum. So this is what Ashish was telling that, okay. So this is x momentum. This is the balance for x momentum only. You can see this second suffix indicates a direction of momentum. X, everywhere it is x actually, and first suffix indicates its component. So this is the z component of x momentum, this is the x component of x momentum, this is the y component of x momentum. Okay, so this is the phi xx at x. This will be a momentum x component of x momentum coming in the differential shell. This is phi xx at x plus delta x. This will be a x component of x momentum going out of the differential shell. This will be phi yx at y. This will be y component of x momentum. Y component of x momentum coming in my differential shell. Similarly, this will be phi yx. This will be a y component of x momentum going out of differential shell. Similarly, this will be phi xz, phi zx. Phi zx is the z component of x momentum coming in my differential shell, and this will be a phi zx, z component of x momentum going out of this differential shell. And this for x component, this will be the surface area. For x component, delta y into delta z will be the surface area. For y component, delta z in delta z into a delta x will be the surface area, and for z component it will be delta x into delta y will be the surface area. This will give me rate of momentum coming in minus rate of momentum going out plus forces acting because of gravity. So I will be taking a gravitational force in x direction because I am taking x momentum balance. Okay, here I am taking x momentum balance. So gravitational force in x direction, say gx. If gx is a gravitational force in x direction, so what will be the force acting in x direction? Here roll number 19. Roll number 19.
Yes, sir.
Avinash, so if gx is a gravitational force in x direction, what will be the forces acting in x direction because of gravitational force?
Sir, mass into gravity. So
Mass into gravity.
Density into volume, rho
Ah.
into dx into delta x into delta y into delta z into gravity.
Okay, into gx. That will be, so
Yes, sir,
input
G.
is there, output is there, now accumulation is also there, so you can arrange everything. So net rate of momentum because of a velocity in x direction. So I am taking x momentum balance. So this you can see, this is the rate of momentum coming in, this is the rate of momentum going out, and these are x component. Okay, momentum coming in, going out in x component, and surface area will be delta y delta z. Similarly, this will be a rate of momentum coming in. This is the rate of momentum going out, y component, and delta z, delta x will be the, you can say, surface area perpendicular to this y direction. Similarly, this is z component, rate of momentum coming in, and this is the rate of momentum going out, and this is the surface area delta x, delta y. Okay, so this will be a overall rate of momentum coming in minus going out, a total forces acting on an element, and say gx is a gravitational force in x direction. Gx is a x component of a gravitational force. Mass into acceleration, this will be delta x, delta y, delta z is a volume. Volume multiplied by density is a mass. Mass into acceleration is a force, actually. And similarly, accumulation, how I will get? I will get delta x, delta y, delta z multiplied by density will give you a mass. Mass into velocity, Vx will be Vx, and variation of this quantity with respect to time will be accumulation. Now rearranging this equation, substituting in overall shell balance equation, and dividing it by delta x, delta y, delta z, and delta x, delta y, delta z tends to 0. What differential equation you will get? So you substitute this here. This will be this. This is what this equation is: rate of momentum in minus out. This is external force acting on a plate. Similarly, rate of increase in the momentum will be dou by dou t of rho into delta x, delta y, delta z into Vx, and divide this equation by delta x, delta y, delta z, and taking differential delta x, delta y, delta z tends to 0, and using the definition of differential. So which equation you will get? Roll number 23, Kaushik.
Yes, sir.
So which equation you will get?
Sir, like after dividing by delta x, delta y, delta z. Hello.
Yeah.
Yes, sir. Like rho into dou v by dou t is equals to dou of
So rho into dou v by dou t.
yes, sir.
Dou rho and dou v.
Sir.
So delta x, delta y, delta z, and taking delta x, delta y, delta z tends to 0. So you should be getting this actually. Dou by dou t of rho into Vx. So accumulation will be a rho into Vx into delta x, delta y, delta z, and variation, this d by dt of this, that will be accumulation, and this will be minus property at x plus delta x minus property at x divided by delta x. That will be a definition of differential equation. So this will be a dou by dou x of phi xx plus dou by dou y phi yx plus dou by dou z of phi zx plus rho gx. Are you getting this, Kaushik?
Yes, sir. Yes, sir.
Roll number 24.
Yes, sir.
Are you getting this equation?
Yes, sir. By dividing delta x, delta y, delta z, I got, sir.
Okay. So this is clear now how you are getting this?
Yes, sir.
Can you just explain how you got this?
Sir, it is an accumulation term.
Okay.
Accumulation term is
Accumulation
the
of momentum. Accumulation of
Yes, sir.
momentum.
accumulation of momentum in a shell momentum balance. It is a delta x into delta y into delta z into rho into del vx by del t.
Okay.
By doing equation or by dividing delta x, delta y, delta z on both sides, after substituting in shell momentum balance, I got the equation.
So this is, what is this equation? This is the generalized shell balance equation for x momentum. Okay, because here x velocity. So I am considering x momentum. This is generalized momentum balance for shell balance equation for x momentum. What is this equation is? Generalized. So I am considering Vx and its variation in all three directions. So this will be a generalized shell balance equation for x momentum. Similarly, I will get a generalized shell balance equation for y momentum, generalized shell balance equation for z momentum. So what will be generalized shell balance equation for y momentum? Roll number 25.
Yes, sir.
What will be the generalized shell balance equation for y momentum?
Dou by dou dt rho into Vy is equal
Very
to
good.
minus of
Minus.
dou x into psi into x into y, die of dou.
Okay. What is this term? What will be this term?
That momentum in x is the changes to y in the last second step.
What will be this term completely? You tell me. What will be this term completely?
Dou by dou x into psi into xy.
Dou by dou x of phi into phi of
xy.
xy. Very good. Plus dou by dou y of phi of
Phi of 5 in like yy.
yy. Very good. Plus dou by dou z of
5 into zy.
zy. What will be this term?
Rho gy.
Very good. Rho gy. That will be a generalized shell balance equation for y moment. Roll number 28.
Yes, sir.
So what will be generalized shell balance equation for z momentum?
Dou by dou t of rho vz is equals
good.
to minus of dou by dou z of
No.
x.
Dou by dou x.
Yes, dou by dou x of phi xz
Very good.
plus dou by dou y of phi yz plus
Very
dou
good.
by dou z of phi zz
And
plus
plus
density into gy. Sorry, gz.
very good. So this is the x momentum balance equation. So similarly, this will be a y momentum balance equation. Okay, shell balance equation for y momentum, and this will be a shell balance equation for z momentum. So now you can see. So I need to solve these three equations simultaneously. If I have more than one velocity, say I have Vx, Vy, Vz, and all three velocity varying in all three directions. So I need to solve these three equations. Okay, three three-dimensional equation. First of all, these are three-dimensional equation. It is varying in x direction, not three-dimensional, four-dimensional. It is varying with time also. It is varying with x, y, z. So this simultaneously I need to solve. Okay? And it is very difficult to solve this. You will need a more, at least there should be a 6 boundary condition for Vx, 6 boundary condition for Vy, 6 boundary condition for Vz, and with respect to time, 1 boundary condition for Vx, 1 boundary condition for Vy, 1 boundary condition for Vz. So in all, to solve this, you need a 21 boundary condition if I have Vx, Vy, Vz, and it is varying in all three directions. So analytical solution for this differential equation is next to impossible. Nobody is able to give a analytical solution for differential equation. Analytical solution means model equation which will give me velocity Vx, Vy, Vz directly. Okay, so analytical solution is not at all available. Hence, generally people will use a different numerical technique to solve these three equations simultaneously to get a Vx, Vy, Vz. Once we have this velocity profile, then certainly we can get all the important property like flux profile, drag force, shear stress, all design important property in momentum flux can be estimated. Hence, people are solving these three simultaneous differential equation using numerical method, and whole complete subject is devoted to solve these three equations. And that subject is called as a computational fluid dynamics. So most of the topic in computational fluid dynamics are covered to solve this three differential equation. This three differential equation, whatever techniques used, whatever numerical methods used, what are the advantages of different numerical method, disadvantage, and which method is good, which parameter is important, that everything is covered in that computational fluid dynamics, because analytical solution is not available for this. Okay, so this is equation of motion. So this is equation of motion. You can say this is the first form of equation of motion. Now I know that phi is a component which contains two components or three components. Phi contains three components. What are these three components? Roll number 29.
Sir, phi will be that rho v into, basically for phi xz we can write rho vx vz plus p into delta plus tau xz. So the total flux.
I is a total flux which consists of two components. First of all, one will be a convective flux and another will be a molecular flux. Again, molecular flux consists of two components. One will be the molecular flux because of pressure forces, another will be molecular flux because of viscous forces. Okay, so this is what, so this you can write. So now, as I told, okay, importance of mathematics. Now, instead of remembering these three big equations, so you can just remember these three equations, this small equation, rho by dou t of rho vi equals to minus del dot phi I plus rho gi, where I varies from xyz. This is the divergence of phi, variation of x property with respect to x, variation of y component with respect to y, and variation of z component with respect to z, and I varies from 1 to z. So all three equations, you can get back all three equations if you remember the definition of del and how del dot is operated. So you can get back all these three equations. This is the importance of mathematics. Okay, so you can write a larger equation in compact form, easy to remember and easy to handle mathematically also. Now phi, as I told, phi, okay, this is generalized equation. Same generalized equation, dou by dou t of rho v vector represent this v bold represent vector minus del dot phi plus rho g. So this just suffix is removed, generalized, and phi consists of three components. Phi, this will be rho into velocity. It is the convective momentum flux. and this is the molecular momentum flux. This already we have discussed in detail. So this is molecular momentum flux, and this is the molecular momentum flux because of pressure forces. This is the molecular momentum flux because of the pressure viscous forces. Substituting this, as P is a scalar, okay, del dot will operate differently on scalar, and del dot is operated differently on tensor, and del dot is operated differently on vector. Actually, that you need to remember. Substituting this, so what equation I will get? Dou by dou t of rho into V, that will be equals to minus del dot rho VV minus del P. Okay, this is scalar. As this is scalar, so this will be del P minus del dot tau plus rho G. So this is what? This is the rate of increase of momentum per unit volume. Okay, this is the rate of increase of momentum per unit volume. This is called as a convective term. Okay, this is called as a convective term, which will represent rate of momentum addition by convection per unit volume. And this is the rate of momentum addition by molecular transport or conductive transport per unit volume. And this is all external forces acting per unit volume. And this is pressure forces, this is viscous forces, this is convective term, this is accumulation term, and this is pressure gravitational term. Generally, in whenever you are dealing in computational fluid dynamics, so this is called as the accumulation term, this is called as a convective term, this is called as a pressure term, and this is called as a viscous term, and this is called as a gravitational term. Okay, so this is the generalized shell balance equation. Okay, this is generalized shell balance equation. We are not consider anything, only this is valid for all three velocity, and it is varying in all three directions. Okay, so this is what equation we got. Okay, generalized shell balance equation, you can see up. So this is the equation, d by df rho vx. Okay, this equation. Okay, d by dt of rho into vx minus d by dx rho plus, this is a equation we got. Okay, a equation, and this is the definition of total flux, rho into v plus p delta. This is the definition of total flux, and c is this is the definition of a substantial time derivative. Substantial time derivative. Okay, in the previous term we have discussed actually partial time derivative, total time derivative, and substantial time derivative. So this is substantial time derivative, definition of substantial time derivative using these three equation, and this is the divergence of property, a definition of divergence of property. So this will be d by dx of property x if it is a vector. So then d by dy of property y, d by dy of property z component of property. Combine this a, b, c, d, you should be able to get this equation. So combine this a, b, c, d, you should be able to get this equation. Once you got this equation, just using this definition of substantial time derivative, you can write this in this form actually. Okay, try to get this equation. So combining equation A, B, C, and D, try to get equation number 1. Then using equation number 1 and this definition of given in C and D, you can get this equation. Roll number 26, Vijit. Roll number 26. Roll number 30. Money. Roll number 30, Money.
Yes, sir.
So what you are supposed to do? What you are supposed to do?
Substituting B A
Can you switch on your video?
Yes, sir.
Can you show me your copy?
Yeah, doing, sir.
So what you are doing, I am not able to see that. Keep it properly. Next page.
Doing it, sir.
Okay. So are you able to do that? Are you able to get what I am telling? What you are supposed to do? Roll number 31.
Yes, sir.
Did you got what I am telling you to do?
Yeah, doing, sir.
Okay. Anybody not getting what exactly you are supposed to do? Just it's all mathematical adjustment actually. Only the thing is, don't think that this is true for constant density system. Okay, this is not. This is true for constant. This is true generalized equation. This equation is generalized. This equation is also generalized. Okay, try to derive at home. Okay, just I will explain you. So how to do that. So you can see this is the equation. Now what I am doing, I am substituting this definition of total flux here. Okay, total flux. This will be, I am getting phi xx, that will be rho vx plus p plus tau xx. So here p will not be there because delta will be 0. Here p will not be there. And substituting this, okay. So this is phi xx, okay, p plus this thing. Similarly, this will be a phi yx, and similarly this is phi zx. So this is using the definition of total flux. Total flux is a combination of convective flux plus molecular flux, and molecular flux again consists of two components. One will be a molecular flux because of pressure forces, and another is a molecular flux because of viscous forces. Now this is phi xx, this is phi yx, and this is phi zx. Substituting in this equation. Okay, substituting in this equation. Now just open up the bracket. Use the definition of product rule. Use the product rule and open up the bracket, okay, suitably, so that you will be getting this equation. So what here I have done. So this is my first function and this is my second function. So this is my first function. This is my second function. Okay, and similarly this is my first function and this is my second function, and this is my first function and this is my second function. So you can see, so this differential is distributed over this p and here, and this is treated as a two function. First function is rho into vx, another function is vx. Okay, now I can use a product rule here. Product rule for differentiation. This is first function and this is second function. And open up this bracket. Okay, open up this bracket. So this is so you can say a rearrangement. Okay, this all these terms, convective terms are brought in left hand side. And then you can see this is LHS you got. Okay, LHS is same actually. No, LHS, RHS you got. RHS is this. You can see. You can see in this equation. So this RHS is rearranged actually. Okay, del P by del X. This thing only LHS I have not got. So first we have arranged RHS. This RHS already we got now. Now this need to be rearranged. This need to be rearranged. You can see this RHS We got it, RHS. Now I need to prove that this equals to this. Okay, this equals to this, but density is not constant. Okay, if you keep this density constant, so you may able to prove easily, or that is not true. Density is not constant. Here also, in this equation also, density is not constant. So can substitute this accordingly. Now LHS, I need to prove this LHS equals to this LHS. Now this is LHS. Now here I have used product rule. In first, this is my first function and this is my second function. Density is not constant. Okay. First function into differential of second function plus second function into differential of first function. Now here, this is my first function and this is my second function. In third term, this is my first function and this is my second function. This is my first function and this is my second function. So open up and rearrange. Okay, rearrange. Now you can see this almost rearrange the equation. Almost rearrange the equation. This term is there only. This term is equals to 0. Why this term equals to 0? Yeah, anybody in the class? Roll number 45, 46. Roll number 46.
Yes, sir.
Why this term equals to 0?
Sir.
Yeah, anybody in the class? Roll number 72.
Yes, sir.
Why this term is 0?
Sir, continuous flow,
Yeah,
incompressible.
or continuity flow. Okay, continuity equation. This is the continuity equation, not incompressible fluid.
Yes, sir, continuity.
This is just a continuity. Okay? Because of continuity, this equation is equals to 0. That is not for compressible flow, incompressible flow. Okay. This is true for anything. Continuity flow, because flow is continuous. Okay, flow is continuous. So this equals to 0. This already we have derived previously itself. That is what I was telling it, why we have discussed that continuity equation. This is continuity equation. Dou by dou t of rho plus dou by dou x of, this is del dot rho v. Okay, del dot rho v. This is dou by dou x of rho vx plus del dou by dou y of rho vy plus dou by dou z of rho vz equals to 0. This equals to 0. This is the continuity equation. Hence, so continuity equation. Hence, LHS equals to rho into dou vx by dou t plus vx dou vx by dou x plus vy dou vx by vy plus dou vz. This actually. So LHS is also true. RHS is also true. Hence, this equals to this. So this equation is proved actually from this equation. So we have proved this equation, same equation. This is another form of equation of motion. Okay, this is another form of equation of motion. Now this is proved. Now using this definition of substantial time derivative and divergence of property. Okay, using this definition of substantial time derivative, this can be written like substantial time derivative of velocity. So you can see this is the substantial time derivative of velocity plus del p plus this is divergence of tau. Okay, this is divergence of tau plus rho g. So this is another form of equation. This is another form of equation of continuity. So this is one form of equation of continuity. So this is x equation of motion. Similarly, we can get y equation of motion. Similarly, I can get z equation of motion. Okay, this is x equation of motion, y equation of motion, and z equation of motion. And this is for cylindrical coordinate system. Similarly, I can get cylindrical coordinate system. Similarly, I can get spherical coordinate system. But okay, now we have derived this equation. We have derived this equation. From this, you can get it this equation very easily. This equation very easily. How to get this equation? So you can write in compact mathematical form and then use the definition of del for cylindrical coordinate system. So you can get back this equation. That is the importance of mathematics. You need not to derive this equation again. This will be the equation of motion for cylindrical coordinate system. This will similarly use the definition of del and its operation for spherical coordinate system. So you can get back this equation very easily. So this is the x equation of motion. And for constant density and viscosity, density and viscosity is constant. So here viscosity is there. Actually, this tau can be related with the viscosity. For constant viscosity means Newtonian fluid, this tau is related with the viscosity and velocity. So and substituting that, so this will be the equation we will get. Rho into dou by dou t of px plus bx. This equation plus you can say mu constant viscosity system. This is for constant viscosity system. Del square Vx plus del square Vy plus del square Vz in xyz plus rho gx. This is x equation of motion, and this equation is called as a Navier-Stokes equation. Okay, generally, we will deal with a constant viscosity system, and generally you will encounter this Navier-Stokes equation for solution to get the velocity profile and flux profile actually, generally. So this is the Navier-Stokes equation for x momentum. Similarly, you can get a Navier-Stokes equation for y momentum and z momentum. Okay, this is for, so you can, this is the compact form of Navier-Stokes equation. This is compact form of Navier-Stokes equation, and this is combined. This pressure and this gravitational force is combined together. This will be combined pressure form. Okay, so equation of motion in combined pressure form actually. So Newtonian fluid and combined pressure form. So this is a general form of equation of motion. So that is what, now this itself is a 9 equation. Okay, so you can get a x momentum in Cartesian coordinate, y momentum in Cartesian coordinate, z momentum in Cartesian coordinate. Similarly, r, theta and z momentum in cylindrical coordinate system, r, theta and phi momentum in spherical coordinate system. So using this equation, I can get 9 equation. 3 for Cartesian coordinate system, 3 for cylindrical coordinate system, and 3 for spherical coordinate system. So you need not to remember all these 9 equations. What you need to remember is this compact form. Rho into substantial time derivative of velocity, that will be equals to del into p minus del dot tau plus rho g. So this you need to remember. So you can get back all 9 equations provided you know the definition of del for cylindrical coordinate system, Cartesian coordinate system, and spherical coordinate system, and how del into del dot and the substantial time derivative is operated. If you know that, you can get all 9 equations. Similarly, for constant density and viscosity, this is the equation. For constant density and viscosity, here there will be change actually. For constant viscosity system, okay, constant viscosity system, this will be the equation actually, constant, and this is the Navier-Stokes equation. Then constant density and viscosity combined pressure form. So I can combine this pressure with a gravitational force, and this will be a combined pressure form. Constant density and viscosity combined pressure form actually. And then this is non-accelerating flow. Non-accelerating flow means this variation with respect to time will be 0. Accumulation is 0. So this will be 0. That will be non-accelerating flow for constant density and viscosity. So you can say this will be a non-accelerating flow, constant density and viscosity. Now here also I can have combined pressure form. So negligible viscous flow. Negligible viscous flow means this forces is 0. okay, are close to zero. Viscous forces are close to zero, so I can neglect that term. And this equation is true for negligible viscous forces. When viscosity of the fluid is very negligible, gases and all, that time you can use this equation of change to get the velocity profile when viscous forces are negligible as compared to pressure forces and gravitational force. So you can neglect this. So this you can see now how many. These are 9 equations. These are 9 equations. These are 9 equations. These are 9 equations. So these are all together 45 equations. 45 equation for cylindrical coordinate system, spherical coordinate system, and Cartesian coordinate system. Just if you remember this one slide, and the definition of del for cylindrical coordinate system, spherical coordinate system, and Cartesian coordinate system, and its operation in cylindrical coordinate system, Cartesian coordinate system, and spherical coordinate system. You can get back all 45 equation wherever, whichever equation is needed. You will not need all 45 equation. You will be needing only one equation out of this 45 equation based on your situation. So if you are handling a non-accelerating flow, so you will be using this. If viscous forces are negligible, then you will be using this. If you have constant density and viscosity, you will be using this. Again, constant density and viscosity, non-accelerating flow, this will be equals to 0. Likewise, you can use this equation of motion and get back whatever velocity profile you are needed for whatever complicated problem. Okay, these are the generalized shell balance equation which we have derived. So all these, okay, this is the Navier-Stokes equation for Cartesian coordinate system. So if you use this, okay, if you use this equation and elaborate this equation using the definition of del, and its operation, so you will get this Navier-Stokes equation for Cartesian coordinate system. Similarly, this will be a Navier-Stokes equation for cylindrical coordinate system, and this is the Navier-Stokes equation for a spherical coordinate system. Okay, Navier-Stokes equation for, and most of the time in chemical engineering, you will be handling the problem with constant density and viscosity. So 99% of the time, you will see that your problem will start with a Navier-Stokes equation, because this is very common. You will be dealing with the water. Most of the time in momentum transfer, you will be dealing with water. Almost 80% of the problem will be dealing with water and water-like fluid. So constant viscosity and incompressible fluid, constant density. So most of the time we'll start our problem, solving the problem with a generalized Navier-Stokes equation, substitute all the information given in a problem and solve the problem to get the velocity profile, whichever needed, and then to get the property, related property in momentum transfer. So this everything is given, all these equations. So this transport phenomena, okay, by BSL, Bird, Stewart, and Lightfoot. So page number, this is appendix page number 8, 46, 47, 48. All these equations are given. So most importantly, you need not to remember all 45 equations. Here I am showing only 9 equations. Okay, these are only 9 equations which represent this one equation. So if you remember only this one equation and how del, definition of del for cylindrical coordinate, spherical coordinate, and Cartesian coordinate and its operation, then you can get back all these 9 equations. Similarly, using this equation also you can get back 9 equations. So this you need to remember only this one slide. Definition of del and its operation for cylindrical coordinate, spherical coordinate, and Cartesian coordinate system. And these are the Navier-Stokes equations. So this is the flow through circular tube. So we'll discuss how to use this equation of change. Already we have discussed this problem. Okay, same problem we'll be discussing now using a equation of change. A liquid is flowing in downward direction under the influence of given pressure difference and gravity. Considering steady state laminar flow with a constant density and viscosity in a vertical tube of length L and radius R, develop the equation for flux profile and velocity profile. This is exactly the same problem we have solved, flow through pipe, using shell balance approach. Now, already we have done a shell balance. Generalized shell balance is done in equation of change. Now we will see how we can get the equation for same flow through circular circular tube using equation of change. Okay. So any difficulty in this equation of change? Anybody has any questions? Any difficulty in this? Yeah, roll number 75.
Yes, sir.
Any difficulty?
No, sir.
94. 4 is not there.
Yes, sir.
Yeah, any difficulty?
No, sir.
For 88. Na? Pritesh. Pritesh.
Hello.
Any difficulty?
No, sir.
Anybody else has any difficulty? Okay, then see you in next class. So we'll discuss how to use this equation of change for solving the problem that we'll be discussing in next couple of classes.